is Ohm's law? Before that, we will show you the introduction of electricity. To help us understand the terms in the said topic, such as electric current, voltage, and resistance, also how are they related?
What is electricity? Electricity is a fundamental form of energy that occurs when there is a positive and a negative polarity. Movement of charged electrons, protons, and ions create electrical energy. Electricity occurs naturally, as with lightning, or can be produced with generators. Current is the movement of electrons from one atom to another atom. The more electrons that pass through a given point in a circuit, the higher current intensity is. Intensity of an electrical current is measured in amperes. What is resistance? Resistance is when a property of an electrical conductor opposes the flow of electricity and causes the electrical current to lose its energy. Resistance is indicated by the letter R and is measured in ohms. An ohm meter is used to measure resistance. Ohms comes from the Greek letter omega. Multimeter. This multimeter measures ohms as well as AC and DC voltage and amperage. Resistor. Resistors reduce the flow of electrical current. The current is reduced as it passes through one terminal of the resistor to the other side. Voltage. Voltage is an electrical pressure needed to produce current. The letter E represents voltage in a system. Various voltages can be run through most motors, whether it's single phase or three phase. What are single phase and three phase currents? Single phase current. Current has a single wave alternating current and can be conducted through a two-wire circuit. This type of electric power supply is found in homes and garages. Voltage ranges from 120 volt to 240 volt. Three-phase current has three circuit conductors. Each circuit conductor carries an identical 60 Hz alternating current. In a single cycle, first one current will peak, then the second and the third currents will peak 1/3 and 2/3 of the cycle later. This provides more voltage with less fluctuation than what could be produced in a single phase current. It is also a more cost-efficient way to run larger motors. A three-phase motor has a low startup amperage drop. Three-phase current is generally found in industrial plants, offices, and manufacturing facilities. Watt is the electrical unit for power. 1 watt is 1 ampere of current flowing at 1 volt. Kilowatts are commonly used when talking about electrical power. 1 kilowatt is equal to 1,000 watts and is expressed as kW. The energy consumed in an electrical circuit is measured in watt-hours. If 1 watt is used for 1 hour, the amount of energy consumed would be 1 watt-hour. The kilowatt-hour, kWh, is equal to 1,000 watt-hours.
Are they related? Anyway, back to our question about Ohm's law. The next video will show us the said topic.
Okay, now we're going to talk about Ohm's law. Ohm's law is probably the most fundamental equation in the whole world of electric circuitry. Anyone who deals with circuits in any way understands and uses Ohm's law on a regular basis. And I'm going to explain this in the context of a diagram of a simple circuit here. And I'll just draw a battery and a light bulb because once again we're all familiar with the batteries and light bulbs. We've seen things like this. So this is easy to understand. Let's imagine a little light bulb here, and we run a wire from the battery over to the bulb, and then from the bulb back to the other end of the battery. And inside the bulb is the filament, and when the current goes through it, it shines. Whenever you have something like this, a circuit element, like this light bulb in the circuit, there are three variables to consider. There's the voltage, and the symbol for voltage is V, capital V. And voltage is measured in volts. So you would say in this case the voltage is 1.5 volts. Or if you have the electrical outlet in your home, you would say the voltage is 120 volts. Unfortunately, the symbol for volts is also V. So you end up writing things like this. You end up writing things like here, V equals 1.5 V, which looks like strange algebra. How can V equal 1.5 times V? That doesn't seem to make sense, but that's not what this says. This is not an algebraic error. This says the voltage, the thing, is 1.5 volts, and this second V over here is the unit. They just happen to have the same letter, but it's pretty easy to tell by the context which is which. So you have the voltage in volts, you have the resistance, and we call that capital R. Resistance is exactly what the name implies. It's resistance to current flow. Everything has some resistance. Well, almost everything. Almost everything impedes the flow of current in some way. And things that you put in the circuit, for example, the light bulb, has a significant amount of resistance. The wires have very little resistance, which is exactly why we use them. In fact, the resistance of the wires is so small compared to the resistance of the bulb that we consider the resistance of the wires to be zero. That's really a good approximation. It's not quite zero, but it's really close. So it's a good approximation to just ignore the resistance of the wires. The resistance to current flow in this circuit primarily comes from the bulb. And anything that you put into the circuit, you could put a light bulb there, a heater, a toaster, anything has some electrical resistance. And resistance is measured in ohms. OHMS, and you recognize the name ohm there. We'll talk about George Ohm in just a second. Resistance is measured in ohms, and the symbol for ohms is the Greek letter omega. This is the last letter of the Greek alphabet, and it looks kind of like a horseshoe like that. So you might say something like this. You might say resistance equals 6 ohms, or the resistance equals 1,000 ohms. That's just how that symbol is used. And then the third thing to consider is the current. And the symbol for current is I. The letter C is used for other things, so that's not the most convenient or intuitive symbol, but just roll with that. Just take that as a fact. Current is commonly represented by the letter I, and it's measured in amps. And the symbol for amps is A, which is kind of nice. That makes sense. Sometimes you hear the term, instead of amps, you hear amperes, and that's the correct term. This is named after a person, André Ampère, a French physicist who did a lot of work with electrical theory at the time this was being discovered. And amps is just short for amperes, and you hear it said both ways, amps or amperes. So someone might write, for example, the current is 5 amps, or they might write the current is 20 amps. That's just how the symbol I is used, and the A is used in this context. I is the current, and it's measured in amps. Amps is the unit. Now, here's Ohm's law. These three things, the voltage, the resistance, and the current, are all related by a nice simple mathematical equation. And this is it. V equals I times R. V is the voltage, I is the current, and R is the resistance. And this equation is known as Ohm's law. And it's not really a law in the sense that it's universally applicable like other laws of physics, but it does work incredibly well for most conductors across a wide range of temperatures and conditions. So this does accurately describe the way things behave in the real world. The voltage flowing through something is always equal to the current times the resistance. Now here's a picture of George Ohm. This guy was a school teacher, and he was conducting electrical experiments, and this was soon after the electric battery had been invented. And before the electric battery, people were only able to do experiments with static electric charges, and they had these little devices called Leyden jars that they could use to store up some pretty big static charges, but it would discharge real quickly. They couldn't do experiments with any sustained current flow. Once the battery was invented, and that was in the year 1800, that allowed scientists and physicists to begin to experiment with a continuous flow of current. And Ohm discovered this in his experiments, this fundamental relationship between the voltage and the current and the resistance. And as I said before, it's one of the most important and most fundamental equations in the study of electric circuits. Now I want to say one more thing about the equation. Ohm's law, which is commonly written like this, V equals IR, can be rearranged algebraically. What if I divided both sides by R? And then you see over here on the right side, the R up top and down below will cancel, and I'm left with I equals V over R. So let's write it like that. I equals V over R. The equation makes a lot of sense if you think about it this way. Remember, well, let me write it over here. I equals V over R, and this is just the original equation, V equals IR, just rearranged algebraically. So I is the current, V is the voltage, and R is the resistance. So think of voltage, remember. Voltage is what motivates the current flow. You increase the voltage, that causes more current to flow. And resistance is that which opposes the current flow. So if you put in something that has higher resistance, that will interfere, that will impede and cause lower current, a lower amount of current to flow. These facts show up mathematically in this equation. You can imagine putting two numbers in here and doing the math, just a division, V divided by R, and getting out a number for I. And this makes sense. If you put in a big number for V right here, then when you do the calculation, you'll get out a bigger number for I, for the current. And if you put in a big number for the resistance, then when you do this calculation, you'll be having a large number be dividing by a large number down here in the denominator. So you'll end up with a smaller value for I. So this makes sense. Increasing, if you understand that voltage is what causes current flow, then you understand that increasing the voltage causes more current. And so putting in a bigger number for V there gives you a bigger number for your current. And if you understand that resistance is interference with current flow, you understand that putting in a bigger number for R will give you a smaller number for current when you do this calculation. So this equation makes a lot of sense, and it also matches what we see in the real world. And that's fundamentally the test for whether or not something is true in science, is does it in fact fit with the actual data that we see in the real world? And in this case it does. Ohm's law, I equals V over R, but more commonly written like this, V equals IR. And we'll come back next and do some simple example problems with this equation.
But how can we use Ohm's law in our lives or in situations? The next video will show us how can we solve different problems or situations.
We're still talking about Ohm's law, which is commonly written as V equals IR, and we're going to work through three simple example problems with Ohm's law. Now, even though it's commonly written this way, remember that there are other ways we can write Ohm's law. We could take the equation V equals IR, and we can divide both sides by R, as we did before, and when we do that, the R's cancel out on the right, and that leaves us with an I on the right equal to V over R. So instead of being written like this, V equals IR, it could also be written like this, I equals V over R. And there's another thing we can do. We can take the equation V equals IR, and we can divide both sides by I. And when we do that, the I's on that side cancel out, and we're left with R equals V over I. So Ohm's law could also be written like that. R equals V over I. These three equations are all mathematically equivalent. They're all really the same equation, just algebraically arranged differently. And we'll do an example problem with the equation in each of those three forms. Here's the first one. A 12-volt battery is connected to a light bulb with a resistance of 3 ohms. How much current flows through the light bulb? Well, the 12 volts, when it says there, that's the voltage. So I'm going to write V equals 12 volts. And it's connected to a light bulb with the resistance of 3 ohms. So that's the resistance, so I'm going to write R equals 3 ohms. And you see the symbol omega is the symbol for the resistance, for the unit of resistance, the ohms. And we're trying to find the current. How much current? So I is what we don't know. We can use the equation in this form. I equals V over R. And we just put in the numbers that we know for V. V is 12 volts, R is 3 ohms, and when we divide we get 4, and the current is in amps, and we use the symbol A for amps or amperes. In this example, we're told that a large electric heater is designed to draw 40 amps of current. And 40 amps is a lot of current. Just to give you an idea, I hooked up a meter to my stove. I have it's a regular electric stove with 4 burners, and I put them all on high. And with all burners on high, it was drawing 28 amps of current. So, and you typically don't run the stove with all 4 burners on high, but that gives you an idea of how much 28 amps is. Your electric stove, turn everything on high, that's it. So this is 40 amps of current. That's a large heater. All right, let's look at the problem. If the resistance of the heating element is 5.5 ohms, so that's the resistance R, 5.5 ohms, and we're also given here the 40 amps, that's the current. So I'll write I for current is 40 amps. And we're asked how much voltage. The voltage is what we're looking for. So we just use the equation in this form, V equals IR. So it's just a simple multiplication. 40 amps times 5.5 ohms, and it comes out to 220 volts. That's our answer. Now that's a lot of voltage. Now you might remember I said that a regular electrical household outlet has 120 volts. Or sometimes it's 110. So one of these outlets on your wall that looks like this is 120 volts. So you obviously couldn't plug this heater into that outlet. You need it to match. This heater is designed to use 220 volts. But if you go in your house and you look, say, behind your dryer uses a lot of electricity. There's a heating element in there and a big fan, and it takes a lot of energy to heat those clothes up enough to dry them. And there's a plug probably on the wall behind the dryer that looks something like this, and it's got 3 holes right there. And the plug on the back of your dryer that you plug into the socket is shaped to fit there, and it won't plug into a regular outlet. This is a 220 volt outlet, and most people have one of those in their home, and this is a 120 volt outlet here. So this, you could have a heater that runs on 220 volts, but you would need to plug it into a 220 volt outlet like this. Most of the stuff in your home, though, goes on the regular 120 or 110. And one more. When a certain light bulb is connected to a 1.5 volt battery, okay, so that's our voltage, V is 1.5 volts, 0.25 amps of current flow, so that's the current, and I is our symbol for current, and it's 0.25 amps. 0.25 amps of current flow through the bulb. What is the resistance? The resistance is what I don't know, so I'll use the equation in this form, R equals V over I, and I put in 1.5 volts and 0.25 amps, and I do the division, and it comes out to 6. And when you divide volts by amps, you get ohms. So this is 6 ohms. That's the resistance in this particular case.